Okay, these are Lewis acids. Are Lewis acids ranked in the acid chart that I gave you, or in the PowerPoint yesterday? Are those Lewis acids there? No. I mean, the chart I gave you ranks the Bronsted acids, not the Lewis acids. And so you might ask, where's the chart for the Lewis acids? And what would I say? Wikipedia? No, there's no Wikipedia. It would be nice if they had a chart. They have sub charts, you know, sub levels, but the ranking for Lewis acids depends on what you reacted with. So, for example, iodide might prefer lead ions, whereas some chloride, you know, it depends on the bonds that result. And when we try to understand the bonds, this is why we need the orbital stuff, because it depends on how the orbitals overlap. Right? Did I talk about hard, soft, acid, base? Did I? Okay. How well the orbitals overlap is all quantum mechanics. And somebody actually, the professor at UCSB, as a matter of fact, who was there when I was there, tried to come up with a simple way of understanding how the quantum mechanics of orbitals are. And then that is, we came up with this whole concept of hard and soft. You know? Basically, that's going to be beyond the scope of this class. So if somebody were to ask you to rank Lewis acids, we don't really rank them that much. You could use certain things to rank them, like the more positive, the stronger the acid you would expect. The more negative, you know, the more concentrated negative, the stronger the Lewis base you'd expect. Right? The more delocalized that positive or negative is, the weaker you'd expect it to be. We're going to deal with a subset of Lewis acid-base reactions when we talk about complexes. And we'll talk about that in chapter 24. So I'm going to leave Lewis acid bases for now. These are two different ones that we did. One example of Lewis acid, another of Lewis base. But we're going to see a lot. And the ones that we're going to see are all deal with the same type of acid, a metal cation, and different kinds of base. So there we can kind of rank the bases because they're all attacking a similar acid. But in general, we have many different kinds of acids, and it's very hard to predict. And so we need more understanding of bonding. So we're going to move on to the third type of reaction, and that's going to be oxidation reduction, or redox. And so let's look at PowerPoint 3. So in Chem 4 and Chem 1A, most people deal with 1, 2, and 5, not 3 and 4. 1 is single replacement. In fact, last semester I skipped single replacement entirely because the problem with single replacement is this. How many single replacement patterns did you learn? A lot of people tell me they learned 1, A plus BX. If you learn 1, A plus BX, that's not enough. You need a minimum of 2. But even 2 is not enough. Because there are a lot of reactions that fall outside this pattern. And so single replacement is not, you know, as you go on in chem, there are just more and more exceptions you have to memorize, and it becomes less and less useful. And so there's a much more general method, a much more comprehensive method. And so instead of teaching or talking about single replacement, I substitute it with the chart method. In the chart method, you just have a set of procedures, a set of steps that works for everything. And you don't have to memorize any exceptions. It doesn't work all the time, but it works much more than single replacement, so much more that pretty much works for most things we encounter. Combustion reactions, we still have those. When we're doing combustion reactions, we typically look at combustibles, like organics. One thing those have in common is they're all electron rich. And so if we're looking at combustion reaction, like methane, methane is highly flammable. And we could react it with oxidizers like oxygen. Oxidizers, what do? They take electrons. So methane, something like methane must be electron rich. When I look at methane, it looks electron rich to me because of the oxidation state on carbon. What is the oxidation state on carbon? Got it. What is it? -4. It's pretty electron rich. -4. But, so we take methane plus O2 yields water and carbon dioxide. So you memorize that pattern. What if somebody threw a variation into this? And you might have seen something like this. Is oxygen the only oxidizer around? No, there are many other oxidizers. Can you name another oxidizer in addition to oxygen? Fluorine. So rather than combusting it, do we need oxygen to combust? No, we could use a different oxidizer like fluorine. Fluorine's an oxidizer because fluorine wants electrons. How about something like CO2? Would CO2 be a potential oxidizer as well? Well, what's the oxidation state on carbon in CO2? +4. So when I look at these two, I see carbon in the -4 and I see carbon in the +4. They're at the opposite ends. In fact, what does the oxidation state for carbon range from? Can you tell me it ranges from plus what to minus what? What's the total range of oxidation states observed for carbon? Yeah, it ranges from -4 to 4. So if we look at carbon, if carbon has a -4 charge, that means it has 4 extra electrons and it's completed its valence shell. Total of 8, right? If carbon has a +4, then it's lost all its valence electrons. And so the range of oxidation states will be from +4 to -4 for carbon. And in fact, if we look at this carbon, would you classify this carbon as electron rich or electron poor? This is pretty electron poor. So if I were expecting CO2 to do something, I'd expect it to be a oxidizer. In fact, you should never use CO2 to extinguish a fire. Well, I shouldn't say that. You could use CO2 to extinguish some fires, but other fires you don't want to use the CO2 fire extinguisher. What are the other fires? Metal fires. You never want to use CO2 on a metal fire. Why? Because this. If you want to put out a fire, you try to smother it. Smothering a fire means not giving it any oxygen, right? It needs oxygen to burn. But putting CO2 on a metal fire is like feeding the fire oxygen. Because CO2 is an oxidizer, oxygen is an oxidizer, you're just feeding it more. In other words, you're fanning the flames. You heard that? Why metal fires? Because metals are highly electron rich. If you have metal like sodium or even magnesium, if you have metal like magnesium, electron rich. I don't know if you've seen this. Maybe I tried to show this in 1A. Let's take a look. Somebody asked me about the YouTube. This is the YouTube here. Get the other. I know.
So here's a nice little demonstration you can do. And it bridges the gap between an understanding of a reactivity series that contains only metals, and one that contains non-metals as well. You'll need some dry ice. You can obtain it from regular cryogenic or gas suppliers, and it comes in 10 kilogram blocks like this. A regular wood saw will be able to cut through the block, but you've got to be patient because they're quite brittle. The last few centimetres will be hard going, but don't rush it too quickly, otherwise you may risk breaking the block. Cut off a lid with an inch or so to play with, and then chisel out a cavity into the body. Again, go easy with it, because you'll likely fracture the block if you hit at it with the chisel rather than scraping it. Eventually you'll end up with something that looks a little bit like this. You can use these blocks more than once, so potentially you could actually team up with other teachers in the department and run a series of these experiments on the same day. Let's see what happens. Don't be tempted to fill the cavity too high, otherwise you can get sparks of magnesium that will fly out through the edge as you start to put the lid on. This experiment is being performed in a fume cupboard because of restrictions where we filmed it. At school it can be done in the open.
Okay, this is the wrong video. But basically, I have another video that didn't come up. But there's no oxygen here. Because the magnesium is burning with CO2. CO2 is the oxidizer. And so sometimes we don't need oxygen to support combustion. We could use other oxidizers. So for example, if magnesium burns with CO2, what's going to form? So magnesium solid burns with CO2, what forms is, well, if magnesium burns in oxygen, what do you think forms? Probably magnesium oxide. And so here, what we're probably going to get is magnesium oxide and maybe carbon monoxide, maybe soot. Actually, we end up with soot there. And so if they lift that lid up and you look inside there, there are a whole bunch of black particles in there, which is just carbon particles, soot. So this is not balanced here. And so this is a different, if there were no carbon here, we just end up with magnesium oxide, but since there's carbon here, this is what we end up with. And so some variations that you might see with combustion to make it more complex is like this. We're going to burn it in an oxygen-free environment. In fact, we're going to use fluorine. Fluorine turns out to be a much more powerful oxidizer than oxygen. Fluorine is, because I was working with fluorine gas for quite a while, fluorine, to give you an idea, can catch stainless steel on fire. You know, stainless steel is very resistant to corrosion. But if we burn methane in an oxygen-free environment with fluorine, will it combust? Yes, it will combust. But what do we form? We aren't going to form CO2 and water because there's no oxygen. And so rather than forming CO2, what will we form? This is a homework problem, by the way. I forgot if it's 1B or 1A. In Petrucci. There's no oxygen, so we can't form CO2. There's no oxygen. So the oxygen isn't converted into oxide, quote unquote. And we're going to have CF2, carbon difluoride. No, it's not CF2. It is going to be CF. How many bonds does carbon like to form? So it's going to be CF4. So we're going to form CF4. And that is if we do complete combustion. Now, the carbon's going to be +4, fluorine's -1. And rather than H2O, we're going to make H2F. Does H2F sound right? No. We're going to form HF. And then we just balance this. And so this is a combustion reaction with a twist, because normally when you do a combustion reaction, it always forms the same thing, CO2 and water, right? But if we use something like fluorine instead of oxygen, then we should get something like this, CF4 and HF. Sometimes what we burn has other elements. So for example, if we burn thiol, did I tell you about thiols, sulfur-containing organics? They smell really bad, but if I have a sulfur in here and a hydrogen and a carbon, would I get CO2 and water? No, I would get CO2, water, and what would the sulfur be converted into? So if you completely burn sulfur, what do you think you form? SO, SO2, SO3, SO4. What do you think you'd form if you burn in oxygen? Like a carbon, hydrogen, sulfur-containing compound. SO2. Possibly SO. Actually, what does the oxidation state on sulfur range from? Plus what to minus what? Yeah. If I go over here, I look at the sulfur, the oxidation state is going to range from +6, if it loses all 6 of its valence electrons, to -2. So SO2 would be sulfur in the +4 oxidation state. And so SO2 is +4. We could actually go to SO3, which would be +6. This is like, with methane. Methane, when we burn it in oxygen, could form carbon monoxide at +2, right? Or it could form carbon dioxide at +4. But could it form carbon trioxide? Is carbon trioxide possible? No, because that would be +6. 6. What's wrong with plus 6? Well, we've taken all those valence electrons, and then what are we going to do? At plus 6, we're going to take its last remaining core electrons. Carbon's going to have 0 electrons. Is that stable? No, not at all. But over here, sure, we could go to SO3 because that's plus 6, right? How about SO4? No, we wouldn't go to SO4 because that would be plus 8. That's not going to happen because that's going to take what kind of electrons? Core electrons. Do you guys remember the ionization energies? Valence electrons versus core electrons. Core electrons are going to have ionization energies twice as big as valence electrons, 10 times as big as valence electrons, 100 times as big as valence electrons, 1,000 times as big as valence electrons. Core electrons have ionization energies how many times bigger than valence electrons? Somebody? Well, what most people do is they look at the ionization energy chart and say, oh, there's a whole bunch of numbers there. There's no way I'm going to memorize those. But did you see the pattern? Did you see a pattern between ionizing valence electrons and ionizing core? How much more energy was it to ionize a core electron? And then the diagram had a little boundary. Remember that? And so how big was that jump? You know, so you don't memorize individual numbers, but you should memorize some kind of pattern. And that pattern was, it was about, and it was pretty consistent. You know, when you went from valence to the core, it was this big of a jump. It was ultima. You remember? Not twice. Successive valence electrons were twice. So ionization 1 versus ionization 2. Ionization 2 is typically twice as big as ionization number 1. And so successive ones were doubled usually. Rough, you know, these are all crude. These aren't exact, but these are patterns. 100 times is too big. Too big. It was about 10 times. Yeah. 10 times as much energy. Which means it's not impossible, but it's unlikely because it just costs too much energy, right? Yeah, a lot of things are. You know what I was using fluorine for? I was using fluorine when I was a student at UCLA because I wanted to make iron plus 4. You know, because you know iron plus 2, you know iron plus 3. Well, I wanted to make iron plus 4. Iron plus 4 is obviously not stable, but some group, some other research lab said they made an iron plus 4 compound. And so I tried to repeat that work. And so in order to strip that 4th electron, it wasn't a core, I could actually technically use a core because the 3Ds are core electrons, but it wasn't, you know, impossible to strip that electron because the energy wasn't that huge. So, but I had to use a powerful oxidizer, and the oxidizer I used was fluorine to do it. But anyway, let's go back to this. So memorizing little patterns, the reason is it's quite beneficial to memorize little patterns here and there because it really, unless you have an exceptional memory, it really makes, because my memory's awful. And since my memory's awful, you know, I try to remember things by doing that. All right, so we might see more complex combustion reactions in Chem 1B. Maybe, maybe not, depends. You know, combustion is mostly covered in Chem 1A. But we're going to spend most of our time on 3, and a little bit of time on 5, and pretty much no time on 4. And so let's jump to 3. This is the redox chart method. I named this the redox chart method. Why? Because we use the redox chart. This is the redox chart here. And let's see. this method is very similar to the Bronsted acid-base method. We just use, I should have named the Bronsted acid-base the acid-base chart method. Bronsted acid-base chart method. But the procedure is exactly the same. For the redox chart method, you don't need to know, what is the maximum, minimum oxidation state. You don't need to know that core electrons are 10 times harder to ionize than valence electrons. You don't need to know anything. All you need to know is how to use this chart. And so the first thing in using the chart is to take a look at it. So a lot of people will say, yeah. That's mass. A lot of people will say, oh, there's a lot of stuff here. And so this is part of the, the data reduction process. The data reduction, you've got a lot of data here. How can you reduce it? How can you reduce it into what? How can you reduce it into more simpler patterns to remember? I don't expect anybody to memorize this, although people have asked me. I don't know if they're serious or if they're joking, but there's no way I'd memorize this. Because this isn't even comprehensive. There's a bigger chart in your appendix D. Right? Even if you're memorizing this, you're missing some stuff. But anyway, we look for patterns so that we can get an idea. If something doesn't occur on the chart, where can we place it approximately? And understand. For example, CO2 doesn't occur on the chart, but I can get an idea of roughly where I might place it. In that respect. And so we look at entries. On the left side are the oxidizers, and on the right side are the reducers. We only need one chart here because there's a conjugate relationship. Oxidizers want electrons. So we got fluorine. Fluorine really wants electrons. So it takes them. Forms fluoride. And so fluorine is the oxidizer. Fluoride is the conjugate reducer. If fluorine's a very powerful oxidizer, then the conjugate reducer is very weak. The reason is once fluorine gets those electrons, it doesn't want to let go. Reducers must lose their electrons. And so fluoride does not want to lose its electrons. And so we have this conjugate. And so what we should do is we should learn the limits. Fluorine's the most powerful oxidizer. What's the most powerful reducer on the chart? Well, actually, before I do that, we should know the most powerful oxidizer. What's the weakest oxidizer on this chart? So I go down the list and I'm here, but then there's this subtable here. So is the weakest oxidizer water, or is the weakest oxidizer lithium ions? Weakest oxidizer is lithium ions. So where does water fit in? Why is water at the bottom of the chart? The reason I'm bringing this up is because on exams people come up and ask me, what's going on here? I don't understand what's. Well, haven't you looked at it before? Not really. So I get that a lot, but I expect everybody to know what's going on here. If water is not the weakest, then where does water belong? And so this requires looking at this chart. When you look at this chart, then you'll see these numbers over here. We aren't going to worry about these numbers. These numbers are for later. We get to electrochem. But we look, for water has a number 0.828 negative. And so actually water fits in up here. It's between negative 0.763 and negative 1.6. So it's between these two. If water's in between these two, then what that tells me is that water is a weaker oxidizer than zinc 2+, but a stronger oxidizer than Al 3+. And so that's where water fits. And in fact, that's where all these species fit. The reason they took these species out is because up here, these are for basic and neutral, and acidic and neutral. And these ones down here are for basic, but we can just fit them in there. All right, if the lithium ion is the weakest oxidizer, then its conjugate must be the strongest reducer. Lithium ion really doesn't want electrons, so that once it gets an electron to form lithium metal, it wants to get rid of that electron. That's one way of thinking about it. Or, in other words, lithium has the lowest ionization energy. Or does it? Because, you know, ionization energy is how much energy it takes to take that electron, right? Does lithium have a lowest ionization energy? No, potassium's ionization energy is lower. Remember? Potassium is a bigger atom, easier to ionize. Lithium is a smaller atom. So there's a bit of a paradox here. And that is, shouldn't potassium be the better reducing agent than lithium? Utama, do you have an answer for that? Why lithium is at the top of the list for reducers and not potassium? You remember? Vaughn, you remember? Well, probably. This is very tricky because it has to do with the stability of the products. The stability of the product. And so when we look at chemical reactions, we have to look at, you know, how reactive things are. Potassium reacts actually much more violently than lithium, but overall result, when you add up all the steps, and it turns out lithium's better because it forms a little more stable product than potassium. But that we're going to talk about later in more depth. I just was curious. But anyway, we just memorized lithium is the most powerful. Do we have to worry about why potassium is less powerful? No. All we have to do is we have to be able to use this chart, that's all. So if lithium is the best and fluoride is the worst. Okay, so using the chart method, that's all. I ask my Chem 1A students, memorize fluorine, memorize lithium. All right. So the process is like this. We inventory the species, find the strongest oxidizer present, find the strongest reducer present. The charts are located in table 20.1 or appendix D. 4, we combine the strongest oxidizer with the strongest reducer. This is a little bit more complicated than combining the strongest acid with the strongest base, because in an acid-base reaction, only one proton is transferred. In a redox reaction, we could have 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons transferred, which complicates things a little bit. And then we simplify. This method yields the NIE. So let's go ahead and do an example here, really quick. We'll do copper solid plus nitric acid aqueous. What does this yield? When you look at a reaction like this, this looks like the A plus BX pattern to me. That is, A plus BX yields AX plus B. What type of pattern is that? That's a single replacement, right? It's only a single replacement, so it's not to memorize. And so I would expect this to form copper 1 nitrate or copper 2 nitrate. Do you know which one's more stable? Copper 1 or copper 2? What should I form? Copper 1 nitrate or should I form copper 2 nitrate? Copper 2 nitrate. How did you know that? I'm sorry? Well, if it's the charge on nitrate, then the copper 1 would be kind of nice because it's just 1 to 1. Nitrate's -1, copper's +1. It works out pretty good. So that's not exactly the reason. How did you know that? Somebody? Lon? Or anybody else? Those are the only two. Oh, Anthony. Hidden way back there. These are the only people I can pick on right now because I don't know everybody's names. Anthony, you remember? Hmm? No. I'll tell you. This is what I said in Chem 1A, but I can understand why nobody remembers. Because what I said in Chem 1A is this: I see copper 2. Do you see copper 1 on the redox chart? Do you? No. So what that tells me is copper 1 very common? Not compared to copper 2. Copper 2 has got to be common. Otherwise, why would they put it in this abridged redox chart? Copper 1 is in the appendix D. And so that means most copper compounds must be copper 2, not copper 1. And so we're going to assume that based on the redox chart, it's going to go to copper 2 rather than copper 1. So we're going to form copper 2 nitrate. Why? I don't know why. We'd have to look at it in more depth to figure it out, theoretically. Actually, there is a reason why, and that's at the end of chapter 24. And so it'll take a while before we get there. But for right now, that's just going to suffice as our answer. And it has to do with stabilizing some of the electrons, the d electrons. And so this is going to form copper 2 nitrate plus hydrogen. We need to balance this. Hydrogen is a gas. Copper 2 nitrate's aqueous. And then for single replacement, for those of you that did single replacement, what's the driving force for single replacement? The driving force for single replacement is going from more active to less active. And so what's more active? Hydrogen or copper? In other words, if you're going to fill up the trunk of your car, you want to fill it up with hydrogen gas, or would you fill it up with copper metal? I'd fill it up with copper because hydrogen is quite active. It's quite reactive, right? Quite unstable. So you wouldn't want to do that. And so what we say is we're going from less active to more active. Therefore, that's not a driving force. We expect no reaction in terms of the activity series. Now, you might have noticed this. When you're looking at patterns, you see something here. Lithium, potassium, calcium, sodium, magnesium, aluminum. Does that register anything in your mind? Lithium, potassium, calcium, sodium, magnesium, aluminum. You know what? I recognize that. You know where I saw that before? That's the activity series, right? It's just flipped upside down. And so this is an activity series that's been flipped upside down. Now, some redox charts like the activity series, so what they do is they put lithium at the top left, and they'll have it ranked in terms of activity. Via the activity series. And so this redox chart looks a lot like the activity series because you see it lithium, potassium, whatever, right? And so what you have to do is you have to be able to orient yourself. This is like, if there's no gravity, which way's up, which way's down. Well, you don't know which way's up or which way's down. And so the same thing with these charts. These charts can be flipped upside down or right side up. There's actually no right side up, right? It doesn't matter which one you want to put on the top. And so the way you orient yourself is you memorize fluorine and lithium. So if fluorine occurs at the bottom right, then you're never going to be confused. Some people always tell me, well, where's the strongest oxide? The strongest oxide is the top left. But if I give them the wrong chart, then the strongest oxide is at the bottom right. And so when they orient themselves left, right, they're always going to be wrong half the time, depending on what I do with the chart. Does it make sense? Yeah, no. And so some charts are inverted, so be careful. But anyway, this is the activity series here, and we see that the copper up there is less active than hydrogen here. The most active element is lithium. All right, but, the A plus BX pattern assumes something. The A plus BX pattern assumes that we're dealing with a mineral acid, not an oxidizing acid. Because here, A is our reducing agent, B is our oxidizing agent, X is a spectator. So if we're dealing with an acid like HCl, HCl and copper, no reaction. Because HCl is what we call a mineral acid. All acids have H plus in common. H plus is an oxidizer. Here, it's a moderate oxidizer. Right? And so all acids are oxidizers. They have H plus. H plus is an oxidizing agent. But oxidizing acids are special because, you know, H plus, sure, that's an oxidizer, but what about nitrate? So if I compare H plus to nitrate, nitrate's a more powerful oxidizer than H plus. So the single replacement format is wrong. The oxidizer shouldn't be H plus. The oxidizer should be X. And so this is why the single replacement format fails for this reaction, because we're dealing with what we call an oxidizing acid. Oxidizing acid has an anion that's a more powerful oxidizer than H plus. Here. So, excuse me. This is nitric acid. It's nitrate and H plus. But if you look at the ratio, it's a 1 to 4. What happened to the other 3 nitrates? The other 3 nitrates turn out to be spectators. And only one of the 4 nitrates is reactive. And it doesn't really matter because we always balance everything at the end. And so we got nitrate and H plus. So we do still need the H plus, but it turns out the nitrate's doing most of the work. The H plus is helping. There's another pattern here. We see a lot. We see H plus, H plus, H plus, H plus, a lot of H pluses. What do all those have in common? You know, these are things that you notice as you see this chart, read through it repeatedly. There are other things you might notice, like this. You know, here's S2O8, 2 minus. Down here is SO4, 2 minus. So why is there such a big difference? Because S2O8 seems like 2 sulfates put together. So if I have a sulfate here and it looks like 2 sulfates put together here, why is there such a big difference? And so this is another odd thing, but it has to do with S2O8, 2 minus. S2O8 is the 3rd most powerful oxidizer on this chart. What makes it so powerful? Especially compared to sulfate. So we look, sulfate, what's the oxidation state of sulfur on sulfate? +6. That's the max. +6 is, this has lost all its valence electrons. What's the oxidation state on sulfur in S2O8, 2 minus? +7. +7 means it's lost all 6 of its valence plus 1 of its core electrons. And so if it's lost a core electron, you better believe this is unstable and it wants electrons, at least 1 more to replace that core electron that was lost. And so this is a very exotic species here, extremely powerful. So what you could do is, and nobody's done this, I've never met anybody that's done this in Chem 1A. For mineral acids, the A plus BX pattern works because H plus is the only oxidizer. For oxidizing acids like sulfuric acid or nitric acid or some of these others, it doesn't. And so what's the pattern? Well, you know, just forget the pattern. We're going to forget patterns and we're going to go to the chart method. And so let's use the chart method to figure out what the products are going to be. In the reaction between copper and nitric acid. All right, so actually, let's take a break before we do that. We'll take a break with about 10 minutes or 10 plus minutes. And then we'll look at using the chart method for this.